Welcome to the ninth example in review of statics. The question reads, find the internal force at point C. And we're given this beautiful diagram right there. Okay, in terms of givens, I don't think there's much you can write here. I'll just say diagram. If we think of any notes, we'll come back. Something that might be useful, like in terms of a formula, is that the centroid, we'll just say centroid of a triangle, or of this type of triangle, right angle triangle, is 2/3 the base. And what that basically means, if I have a triangle like this, and what the centroid means in like a practical, or the definition I explain it with, if I bring my finger and I want to balance it at one specific point where it won't tip this way and it won't tip this way, where will I hold this triangle? For a rectangle, it's simple. Just hold it directly in the center, right? For a triangle or a right angle triangle, it's a bit different. What you want to do is you want to hold it 2/3 the base. So if this is 1/3, this is, this is 1/3, this is 2/3. You want to hold it around here, and this is 3. So if this is in its entirety 9 meters, you want to hold it at 6 meters to perfectly balance it. And that's basically what the centroid means in like these 2D type of shapes. Okay, but that's very important to know. We also want to know that the area of a triangle is equal to 1/3 or 1/2 base times height. That's also pretty important. Okay, we can move on to unknowns. What does the question want us to find? It wants us to find internal forces at point C. What does that mean? Well, since we're in 2 dimensions, we want to see the degrees of freedom at point C. What are the degrees of freedom? We have 3. We have a shear force in the basically y direction, or we can have a normal force in the x direction, so normal, shear, or we can have a moment, right, in counterclockwise or clockwise direction. And we'll check for all of those lovely guys. So VC, NC, or MC. Okay, what can we move on to now? We can move on to the fun stuff, the free body, the free body diagram, yeah? Okay, we have this thing right here. Okay, so we have point A right here, we have point C about here, we have point B over here. The dimensions are as follows. This in its entirety is 12 meters. From here to here is 7 meters. From A to C is 7 meters. We can add our external forces. How are we going to get a resultant force for this triangular distributed load? Well, we're going to go back to our formula right here. 1/2 base times height. In this example, our base is 12 meters, right? This is our base. Base is equal to 12 meters. Our height is equal to 100 kilonewtons per meter. Yeah, per meter. And then 1/2 is equal to 1/2. Okay, so if you multiply those 3 together, you are going to get a resultant force of 600 newtons. Okay, where does it act though? Well, it acts at the centroid of the shape. It acts 2/3 the base. What's 2/3 the base? If I divide 12 by 3 parts, that will give me 4. And if I multiply, and so this is 1/3 the base, right? If I do 2 of that, I get 8. So basically my resultant force is 600 newtons, and it applies at 8 meters. 2/3 the base, and we'll say 8 meters is about right there. So it's 600 newtons in magnitude, and it applies from here to here. This is 1 meter, because if this is 7, this is 1. Okay, perfect stuff. So it's 8 meters away from point A. Amazing. What other forces do we have? We've taken care of the distributed load. How about the other external forces? I see a roller ball connection right here and a pin connection like so. So I have a BY, and I have AY, AX. I'll add those like so. My coordinate system is like that. Okay, very similar to the last problems. How am I going to find by? How am I going to find ax? How am I going to find ay? I'm going to take a moment at point A. It's going to get rid of this force. It's going to get rid of this force. The moments, or the forces that cause a moment about point A, are 600 newtons. And by, I'm going to have one equation, one unknown. I'm going to find by. I'm going to take the sum of forces in ay. I'm going to take the sum of forces in the x direction. I'm going to find ax. Long story short, yeah, we've done this before, so I'll just give you the numbers. So you're going to end up finding that by is equal to 400 newtons. Ay is equal to 200 newtons. And you're going to find that ax is equal to 0 newtons. And they're all positive, so we correctly guessed the dimensions. Amazing stuff. Now we can move on to actually finding the internal forces at point C. We found all the external forces. Now we can look into finding the internal forces. And how are we going to do that? Again, we're going to section the beam. Okay? We're going to just look at this section AC and analyze it. Okay, so we're going to say for section AC. Okay, if section AC kind of looks like so, I have to make it a bit bigger, but it's okay. This is point C, this is point A. In terms of dimensions, we're going to have this entire length is going to be 7 meters. We're going to add a lot more dimensions later on. Well, let's add the forces, okay? So we're going to add AY. We're also going to add AX, okay? What other forces do we have? Well, we section the beam right here, and whenever we section a beam, we have an M and V, right? So we're going to say MC, NC, and VC. And these are the three things we want to find. What are we missing from this diagram up here? Well, you might just jump across, oh, no, there's nothing. But if you scroll up, you see that we have this distributed load that we have to deal with. So you have to remember that this isn't just like, okay, well and done. We still have to account for this, like, because since we section the beam, this force, like the distributed load is still acting on this part of the beam, right? If we take the whole beam into consideration, then we can say, okay, we can summarize this distributed load as a single force acting 8 meters away from A. But since we cut the beam, now we have to recalculate what this distributed load will be, right? And then take a resultant force of that. So let's actually draw on here. I think it would be better drawn here. If this entire force, or this entire distributed load, actually let me draw a hollow triangle. If this distributed load is 100 kilonewtons in magnitude, right? Kilonewtons per meter. And it is 12 meters long. And I want to find a new distributed load. I want to find a new representation for my distributed load right here. Oh, I should not have used the same color. Let's use a different color. I apologize. Okay. I'm going to really mess up this diagram, so copy it. Okay, so that's the one we already have, right? So it's 100. We don't even need the units for now. It's 100 and it's 12 meters long, right? So 100 kilonewtons per meter and 12 meters long. I want to find a new distributed load ending at C. So I'll draw my new triangle like so. And I'll draw it in a nice color like orange. I want to find a new distributed load that I can represent on my AC section right here. This one has a length of 7 meters, right? What can I do? What I want is I want to find this, we'll call it X, for example. I want to find X. I can use similar triangles to find X. I can say that the ratio X over 7 is equal to 100 over 12. And what that will give me, that will say that X, you'll end up getting that X is equal to 58.33 newtons or kilonewtons per meter. And that's how you find this new distributed load. So we'll add that. So it'll kind of look like this. But instead of 100, it'll be 58.33 in magnitude and 7 meters long. Okay, now I'm going to do the exact same thing I did before. I'm going to find the what do you call it? The resultant force. I want to represent it as one single force, but I'm only going to take like this new distributed load into account, and I'm going to see where it acts, right? So I'm just going to use these two concepts again. I'm going to say that it acts 2/3 from the base, so it's going to act 2/3 from the base, and we can even do that right now. We can say where it's going to act. If we take 2/3 from the base, if we divide 7 into 3, we're going to get that it is equal to 2.339, I believe. And if we split this up like so into 3 parts, so this is 2.339, this is 2.339, this is 2.339. Our force, our resultant force from this distributed load will act right there, right? What's its magnitude going to be? Well, as we said before, it's going to be 1/2 the base, which in our case is 7 meters, times the height of the distributed load, which in our case is 58. If you do all that fun stuff, if you multiply these 3 numbers, you are going to get that your new distributed load, or your new resultant force for your new distributed load, is equal to 204.1667 newtons. Perfect stuff. Now, that's your final AC section. What are you going to do now? Well, you are going to take the moment about point C to find MC. How is that going to help you? Well, and I'll actually write this one down, and we'll do it together, actually. So we'll go through the steps one by one. So now we're going to do sum of moments. We want to find MC, NC, and VC. So sum moments. Take the moments about point C, and we say counterclockwise is positive. We get MC. This force will cause a moment, and it is this distance away. And this force will cause a moment, AY, and we know AY from up here, and it is 7 meters away. Or actually, yes, it is 7 meters. I got scared for a second there. Okay, so move this guy a bit down. Minus AY, it's going to cause a negative moment if positive is counterclockwise, plus, we're going to call this, actually, let me just write it down. Just need more space. And from this point on, like you should be able to do by yourself, it's what we've been doing for the last, I think, 3 videos now. And we're going to do it for another 2 videos, unfortunately. Okay. 339 meters. Okay. What you will get from this is you'll get one of your answers. MC is equal to 923.6 newtons times meters. Sum of forces in the y direction. I think I said this is positive, so let's stay like that. 0. The only forces you have in the y direction are a negative 204.17 newtons plus AY, which you know, minus VC. You get that VC is equal to negative 4.17 newtons. And that basically means we assume this direction wrong. It actually acts upwards. Finally, you want to see NC. So you take the sum of the forces in the x direction. You'll get that AX plus NC is equal to 0. You know that AX from before is equal to 0, so therefore NC is also equal to 0 newtons. And these are your 3 internal forces, or your 3, these are all your internal reactions at point C.